Hello everyone, I Rajesh Kanwadia, Assistant Professor from Shankara Institute of Technology in Department of Electronics and Communication. In previous lecture, we have discussed about statement of sampling theorem and proof of sampling theorem. In today's lecture, we will discuss about types of sampling technique. So, there are three types of sampling technique. First one is ideal sampling, second one is natural sampling, third one is Pareto sampling. So, first sampling technique is ideal sampling. So for ideal sampling, first we define input signal, and this input signal is noted by x of t, which is just like a non-sinusoidal continuous time signal. Then after input signal, we define sampling function. So in ideal sampling, we use impulse train signal as a sampling function, which is noted by del tst. And this diagram for impulse train signal is denoted by del tst, and from this diagram we can see that each impulse have pulse width is near equal to 0. Then after sampling function we define sampler circuit. So for ideal sampling we use switching sampler. Its circuit diagram is just shown below. So at the input of this switching sampler we apply input signal, that is x of t, and at the switch position we apply sampling function, that is impulse train signal. So when position of the impulse is high, then switch is closed and these individual pulse are or impulse are multiplied by with input signal, and finally output of this sampler circuit is sampled signal, and that sampled signal is ideal sampled signal. So this diagram of ideal sampled signal is shown below, which is noted by g of t, and pulse width for each impulses is just near equal to 0, which is denoted by tau, and height of the impulses are vary according to instantaneous value of this continuous time signal. So this is graphical representation of ideal sampled signal, and top of the impulses are vary according to the instantaneous value of this input signal, and width for each impulse is just near equal to 0. So this impulse train signal in mathematical form can be represented by as del tst is equal to del t minus nts and summation, which is start from n minus infinite to plus infinite. This sample signal g of t is equal to x of t into multiply by this impulse train signal del tst. So g of t is equal to x of t into summation n is equal to minus infinite to plus infinite del of t minus n ts. And when we apply property of impulse function, and when we multiply this x of t into impulse function by using this property x of t into del of t minus a, then it will become equal to x of a into del of t minus a. So by using these properties of impulse function, this g of t will become equal to summation n is equal to minus infinite to plus infinite x of nts into del of t minus nts. And when we calculate Fourier transform for this ideal sample signal, then its Fourier transform is given by capital G of f is equal to small f of s summation n is equal to minus infinite to plus infinite capital X of f of minus n f s. So this is ideal sample signal in frequency domain. Now, ideal sampling is theoretically possible because it and practically it is not possible because to design a impulse or pulse which have pulse width is near equal to 0, so it is practically not possible. So this is ideal case or theoretical case of impulse sampling. So to avoid that problem we use natural sampling. So second type of sampling technique is natural sampling. So again in natural sampling we define an input signal which is noted by x of t, which is just like a non-sinusoidal continuous time signal. Now sampling function. So after input signal we define sampling function, and for natural sampling we use periodic pulse train, which is noted by c of t of width of each pulse is tau. Okay, so this is periodic pulse train which is noted by c of t, and width for each pulse is just near equal to tau. And then after sampling function we define sampler circuit. So in natural sampling we use natural sampler as a sampler circuit. So it is the diagram of natural sampler. So again at the input of this natural sampler we apply input signal, which that is x of t, and at switch position we apply periodic pulse train. and multiplication of this input signal and periodic pulse trend is just equal to natural sampled signal. So when position of the pulse is high, or we can say when position of pulse C of t is equal to 1, then G of t will become equal to X of t, and when position of pulse C of t is equal to 0, then G of t, that is natural sampled signal, is equal to 0. So this is the diagram for natural sampled signal, and from this diagram we can see that top of the pulses are vary according to the instantaneous value of input signal. So top of the pulses is not remain constant in natural sampler. So this is the drawback in natural sampling. So to avoid this problem, we use flat top or rectangular pulse sampling. So in flat top sampling, again we define a input signal which is noted by this small x of t. Then after input signal we define sampling function. Again sampling function is a periodic pulse trend and pulse width for each impulse is tau. So this sampling function is noted by C of t. After sampling function we define sampler circuit or sampling circuit. So in case of flat top or rectangular pulse sampling, we use sampler and hold circuit. It is the diagram for sampler and hold circuit. So in this circuit diagram we use two FETs which is denoted by Q1 and Q2 and one capacitor which is denoted by small c, and at the input side we apply input signal, that is continuous time signal, and finally output of this sampler and hold circuit is flat top sampled signal. So when a pulse trend is applied at the input of G1 of Q1, then sampling switch is closed for a short duration and capacitor is charged up to a voltage that is equal to instantaneous value of incoming signal, and these charges remain constant until we apply discharging pulse at the input of gate of G2 of Q2. Because the capacitor holds the charge, so capacitor voltage does not follow the shape of applied signal. Thus, the output have flat top sample. So, diagram of flat top sample signal is given by just below, which is showing that top of the pulse remain constant and it is not follow the shape of instantaneous value of input signal because here we use two FET and one capacitor. Okay, so at the one FET Q1 we apply charging pulse, and another FET we apply discharging pulse. So that's why this charging remain constant and top of the pulses remain constant, and which is not follow the shape of the instantaneous value of the input signal. So these are the three types of sampling technique. Okay, so today we stop here. Thank you very much.